Okay, next we have angular momentum of the system of particles. Suppose we have a system of particle, okay, and this is a system in which we have particle, let's say 1, this is particle 2, this is particle 3. Suppose there are n particles, and let's suppose this is the ith particle, such that its position, the position of this ith particle, which I represent by this I, and its mass is mi, and its position from this origin is ri. This is the x-axis and this is y-axis. Now the angular momentum of this ith particle, I can write it here. The angular momentum of ith particle is, normally we define angular momentum as the cross product of r and p, or r cross p, where p is the linear momentum and r is the position vector. The x is from the point from the point is the distance from the point of rotations. Okay, so the angular momentum of ith particle is, I represent it by li, by small capital L. Okay, small l. This is the angular momentum of a single particle. Okay, that's why I use a small letter here, which is equal to ri cross pi, where pi is the linear momentum of the ith particle, where pi is the linear momentum of ith particle. Now let's say this is equation number 1. Now if I have to calculate the total angular momentum of this whole system, about, let's suppose about this point, then I have to sum all the angular momentum of individual particle. Let's say I have particle 1, which is angular momentum L1. I have particle 2, which is angular momentum 2 L2, and I have particle 3, which is angular momentum 3 L3, and so on. So in order to calculate the total angular momentum L, the total angular momentum of the whole system is, like, in order to calculate the total angular momentum of this whole system, which I represent by this capital L, which will be equal to the vector sum of angular momentum of particle 1 plus angular momentum of particle 2 plus angular momentum of particle 3 plus up to angular momentum of particle nth particle. Now this side I can write it in summation form. Let's suppose we have summation or sum over I, such that I started from 1 up to n, and we have this Li. So if I expand this sum, then I get this one, because I started from 1 up to n. So we have L1 and then plus L2 and then plus L3 and then up to plus Ln, because we have n particles in this system. Or we can write the total angular momentum of the whole system is equal to sum over I started from 1 up to n, and we have Li, and Li value is given by this equation number 1. So we have, instead of Li, I will put Ri cross Pi. This is, let's say, equation number 2. This is the angular momentum. This equation 2, I can write it here. Equation 2 shows the angular momentum of the whole system. Now we know that the torque, and we know that I already discussed it before in the case of a single particle, that torque is equal to the rate of change of angular momentum. That is, torque is equal to the rate of change of angular momentum. Okay, so here I have the torque, I have a system of particles, so the torque will be the torque of the whole system. So the torque, or the total torque, acting on the system is given by, I represent it by this capital N, which will be equal to the rate of angular change of angular momentum, dl over dt. But we know that the value of L is given by equation number 2. So here I will replace my equation, I will put the value of L from equation 2 here. So N will be equal to d over dt of L, and L is equal to sum over I, such that I started from 1 up to n, so I am not writing it here. And just keep in mind that the value of I, which is starting from 1 up to n, and we have Ri cross Pi. Now this is derivative and this is the summation, so we can bring this derivative inside this summation. So if I do that, then the torque will be equal to, this torque is a vector quantity, so I have to put a arrow above this torque. So torque will be equal to sum over I d over dt of Ri cross Pi. I can write it like this, sum over I. Now I will apply this derivative to this product. So first I will apply, so I will use the product rule. So here I have dri over dt cross Pi, and then plus Ri cross dpi over dt. Now next, here I have this summation over I, and we know that dri over dt, which is r is the displacement, so rate of change of displacement is velocity. So here dri over dt, I'll represent it by ri dot, which basically shows dri over dt. I can write it here, dri over dt. I represent it by ri dot. This dot basically represent the derivative with respect to time, and this is basically the velocity of ith particle, because this is the rate of change of displacement of ith particle, which is equal to the velocity of ith particle. Now, and then we have cross Pi, and then we have plus Ri cross, now here we have dpi over dt. So dpi over dt, I'll represent it by Pi dot. So this dot here basically represents d over dt, or the time derivative, this dot. So here I have Pi dot. Now I'll apply this summation to each individual terms. So here I have sum over I, or I dot cross Pi, plus sum over I, or I cross Pi dot. Now let's say this is equation number 3. This is the torque, okay? This is equation number 3. Now here I will consider the first term, this term. So consider first term, which is sum over I or I dot cross pi, which is equal to, without that, momentum P, which is equal to mass time velocity. Or we can say that momentum P is equal to mass time or dot. Or dot is basically dr over dt, because velocity is dr over dt. Okay, so this is equal to r dot. Now if I have ith particle momentum, pi, momentum of ith particle will be equal to mass of ith particle times velocity of ith particle, or I dot. So I can replace momentum p by this. I will replace pi by mi into ri dot. So here I have this sum over I or I dot, okay, cross. We have pi, which is mi times ri dot. Now we know that mass of a ith particle, it's a constant quantity, so we can keep it outside of this cross product. So here I left with sum over I. So I'll bring this mass outside mi. So here I left with ri dot cross ri dot. And we know that the cross product of vector with itself, a cross a, is always give 0. So here this term will give us 0. So it means that the first term of this equation 3, which is ri dot cross pi, is equal to 0. Why it is equal to 0? Because the cross product of a vector with itself, because this is a vector ri and this is a vector ri dot, so they are in cross product. Ri dot cross ri dot means a vector with itself. Cross product of vector with itself is always equal to 0. So this term is 0. So it means this whole side is equal to 0. It means that if this is equal to 0, then my equation number 3, or equation 3, now will reduce to, which is n, the torque, which is equal to, this term is now 0, so I left with only this term, which is sum over I or I cross pi dot. But we know that force, we already defined it before, that force is equal to rate of change of linear momentum. F is equal to dp over dt. Now the force acting on ith particle, force on ith particle will be equal to rate of change of momentum of ith particle, dpi over dt. So it means that if I is equal to force on ith particle is equal to dpi over dt, which is basically pi dot. So pi dot will be replaced by this fi. So this equation n will be equals to sum over I or I cross fi. But this is the force, net force acting on the system, because here we have the ith particle, but here it is the whole system, because we have the summation I started from 1 up to n. So it means that we are calculating the torque of the whole system. So this force will be the net force. And we know that the net force acting on ith particle is equal to the sum of two forces. One is external force acting on the ith particle, and the other one is internal force. Sum over J if Ij internal. This is the total force acting on ith particle, which is equal to the sum of two forces. One is external force and the other one is internal force. So here I will replace this net force by this equation. So here I left with my equation n, equation reduced to this is my equation, let's say 4. Then this equation n will reduce to n is equal to sum over I, such that I started from 1 up to n, and we have Ri, okay, cross Fi net, which is equal to Fi external plus sum over J Fij internal. Now I can write this equation like I will apply this sum to each individual term, or I can take a cross product of this with this terms individually. So my torque, this is torque, okay, this is force. So if the force is a vector quantity, so force is a vector quantity, so we have to put an arrow above this force. Now the torque N will be equal to, I will apply this term with cross product with this term. So I have sum over I, here I have Ri cross Fi external plus, we have plus sign, then I will apply this to this one, sum over I, sum over J, because sum over I is this one, sum over J is this one. I have Ri cross Fi J, which is the internal force. I can write it here, N is equal to sum over I, or I cross Fi external plus sum over Ij. This is a double summation, so I will replace it by a single sum with, and this is sum over Ij. Ri cross Fij internal. But here the sum is over I and j, so we will put another condition that I is not equal to j, because the interaction of ith particle with itself is forbidden. We can say that this condition I is not equal to j basically means that ith particle does not interact with itself. A jth particle does not interact with itself. I can write it here where the condition where I is not equal to j, this condition shows that ith particle does not interact with itself. So this is the total torque acting on the system. It has two terms, one is this one and one is this one. So I will stop my video here, and in the next video I will proceed from this equation. Thank you.